All right, so we're starting today a 2-day journey through kind of the last piece of the thermodynamic puzzle, so to speak. We've already talked about thermodynamics from the standpoint of enthalpy and entropy and free energy. Well, electrochemistry isn't going to introduce any new values necessarily. I mean, I guess it will introduce a couple of new terms. But really what we have in electrochemistry is an application of thermodynamics to one particular type of chemical reaction. And it's a type of chemical reaction that we have seen before. We talked a little bit about it in Gen Chem 1. But now we're going to kind of investigate it a little bit more fully. And that's actually what the first topic we're going to tackle in this is looking at oxidation-reduction reactions, redox. Now, like I said, we've seen redox before. We have a little bit of experience with it. We saw it when we did aqueous solutions in Chapter 8 back in Chem 105. And we talked a little bit about oxidation numbers and that kind of thing. We really didn't take it much further than that. And the reason why we didn't take it much further than that was it really wasn't relevant to do so. But now it is. So before we dive with both feet in, let's take a few minutes and kind of just review some of the stuff that we talked about in Chem 105, because there's a good chance that even though this is a summer course and you technically haven't been away from chemistry for that long, it's still been a couple of months at least since we looked at this more fully. So let's just start with the basic terminology here. Oxidation-reduction reactions, otherwise known as redox reactions. These are chemical reactions that take place where we see an electron transfer happening between components of the reactants as they become products. And more specifically, we tend to look at and focus on individual elements changing their charge state in these reactions. We have manganese in a high charge state, grabbing electrons from something else to lower its charge state. And in the process, we get a bunch of different products. Now, the reaction itself is governed by two separate yet inseparable processes. Oxidation, that is, something has to lose electrons, and reduction, something has to gain electrons. Those two processes are independent of each other. The thing that loses electrons is going to be different from the thing that gains electrons. Yet the processes are also inseparable. They're completely dependent on each other. You can't have oxidation without reduction. Nothing just blindly throws electrons out into the sea without knowing that they're going someplace. And similarly, nothing can grab electrons out of thin air. They have to come from somewhere. So these two processes happen simultaneously. One directly impacts and leads to the other. Now, back in Chem 105, we gave you these mnemonic devices to try to help you keep oxidation and reduction straight. And we're going to reiterate them here again. Which one you use, the fact that you use either of them doesn't matter to me. It's all about what goes on inside your head. But it's really easy to get them confused, especially when we start talking about oxidizing agents and reducing agents, which act in complete counter to what we think of as oxidation and reduction. Because an oxidizing agent forces oxidation. So it's not getting oxidized itself, it's causing something else to get oxidized. And since it's causing that thing to be oxidized, it must be the thing that's taking the electrons. So the first device is Leoger. Leo the lion goes, grr. Leoger, we've got the two separate parts. The loss of electrons is oxidation, that's Leo. And the gain of electrons is reduction, that's grr. On the other side, we've got oil rig. Oil rig discusses that oxidation is the loss of electrons, that's the oil, and reduction is the gain of electrons, that's the rig. Now again, which mnemonic you use really doesn't matter to me. When I was in high school and first learned about this, Leoger was the thing that my chemistry teacher taught me. In college, I sat in the same chairs that you're in, well, not these exact same ones, similar ones in Pennsylvania where I went to college. And it was not actually a professor of mine, but one of my classmates said, oh, Leoger, what the heck's that? I know oil rig. What's oil rig? And he told me, oh, yeah, that makes sense. So they're just two different ways of doing it. The point of the mnemonic, though, is to help you remember, help you to keep it straight in your head so that you don't get it confused, because it is easy to get it confused. Now, what you can also remember from Chem 105 is that we can identify oxidation reduction reactions based upon the tracking of electrons, the movement of electrons in a chemical equation. And we do that through the use of oxidation numbers. An oxidation number is a number that is assigned to an individual element to give you an idea of just what the relative charge is on that element itself. Now, oxidation state is different from formal charge being that thing that we associate with Lewis structures to help try to figure out which one kind of is the best. Oxidation states are a little bit more real. They're a little bit less fuzzy. They're not prone to resonance and other things like formal charges are. But what they give us an idea of is, does this particular element have a whole lot of electrons? Does it not have a whole lot of electrons? And that relative number can give you a lot of idea in terms of, what its reactivity ultimately is. So again, just to review, oxidation numbers follow a couple of simple guidelines. The first guideline is that the sum of all of the oxidation numbers in a given element, ion, or molecule have to equal the total charge on that element, molecule, or ion. So for certain things, that makes oxidation states really easy. So if I have elemental chlorine has no charge. So its oxidation state must be 0. If I have the iron 3+ ion, well, that's its charge, 3+. That's also its oxidation state. Where it gets a little bit more complicated, especially, is when we start looking at neutral molecules, like what do we do with carbon dioxide? What do we do with water? What do we do with carbonic acid? And polyatomic ions. How can I figure out the state for manganese in permanganate ion? How can I figure out the state of chromium in the dichromate ion? And so that's where that sum piece comes into play. Because what I can look at it and say is, okay, carbon dioxide, I've got a carbon and I've got two oxygens. I don't know what those oxidation numbers are necessarily, but I know that the sum of those three numbers, the one carbon and the two oxygens, has to equal 0 because the molecule itself is uncharged. And I might not know what the oxidation state off the top of my head for chromium is or for oxygen. But since dichromate is a -2 ion, I know that the sum of all of those numbers after I add it all together has to equal out to -2. So that's the first guideline, and it's kind of the most important one because it gives us that foundation to kind of make us have a way of comparing. Now, the other guideline is also important because it helps us to kind of smooth out when we don't know what to do next. And these are the common oxidation states. So common oxidation states, fluorine. When fluorine is in a molecule, it is going to have a -1 charge. And the reason for that is because fluorine is more electronegative than anybody. And so its ability to draw electrons to itself and at least superficially complete their octet is going to be pretty high. Hydrogen really only has 3 possible oxidation states. When it's in its elemental state, it's 0. When it's bonded with nonmetals, it's +1. When it's bonded with metals, it's -1. Basically, its behavior, because of where it is on the periodic table, because it is listed with the alkali metals, so it does possess certain metal-like properties, like having a positive charge and that kind of thing. When it's dealing with other nonmetals, it's going to take on more of that metallic character. And it's going to take on positive charge. And since it only has the 1 electron to lose, that's its maximum oxidation state is +1. It can't be +2 because where's that second electron going to come from? It doesn't exist. And the same thing, when it's interacting with metals, well, the metallic character of lithium is far greater than the metallic character of hydrogen. So hydrogen is going to act like a non-metal in that case. It's going to take on a -1 charge. But again, it's -1 charge, that's as high as it can go because that first energy level can only hold 2 electrons. And so if it's got its 1 and it's adding 1 more, there's your 2. So the range of states for hydrogen is pretty limited based upon its size and its chemistry. And then finally, oxygen. Oxygen is usually in the -2 state. In fact, most of the applications that we work with oxygen have it in the -2 state. The only exceptions to this rule are if we are looking at peroxides, so like sodium peroxide or hydrogen peroxide, there we've got 2 oxygens sharing that -2 charge, which means that each oxygen is only -1. And the other exception, and it's not listed here, is in compounds like OF2, where the negativity of the fluorine is going to force oxygen to act like a positive charge. Now, oxygen difluoride is not a molecule we're going to deal with a whole lot, but it's an important thing to note. If we have fluorinated compounds that contain oxygen, if there's no other place for the fluorine to get its -1 charge, it'll take it from the oxygen. Otherwise, assume that, if we have COF2, insert a carbon in here. Now they both will take electrons from the carbon instead of from each other. Now, the part of this that we haven't done is we haven't talked any about balancing these reactions. And because electrochemistry is going to be based on these kinds of reactions, we're going to have to spend a little bit of time with balancing here, just so that we can kind of get a sense of where these reactions ultimately come from. So how you balance a redox equation is as follows. The first thing that you need to do is you need to split it into half reactions. Now, the easiest way to identify the oxidation and reduction half reactions would be to assign oxidation numbers to everything and then figure out where the electrons are going. But technically speaking, you don't have to do that step, because if you follow the directions on the next slide, what you're going to see is that one of the half reactions is going to gain electrons, have electrons as a reactant, and the other one is going to lose electrons, have electrons as a product. And so from that standpoint, you could identify the oxidation and the reduction based upon where the electrons are being added or removed. But what you do is you split it into half reactions, you balance each half reaction, and then you combine them in such a way that there's no electrons left over to balance out the charge. And then more than likely in that combination step, there's going to be redundancy. There's going to be stuff that's on both sides of the equation, and you're just going to want to make sure that you cross out any redundancies. So what does that actually look like in practice? Well, the process for balancing the half reactions is as follows. First, we're going to balance every element in the half reaction that's not hydrogen or oxygen. So if I've got a half reaction where I've got iodine, I2 on one side, and iodide, I- on the other, first thing I'm going to do is make sure that I've got two iodines on both sides. The 2 in the I2 and a coefficient of 2 in front of the iodide to give me 2 iodine atoms. So that's the first part that we have to do. Now, not every half reaction is going to require that step. It just depends upon what it is that we are looking at. But after we balance those other elements, the next step is to balance the oxygens. We balance oxygens in a half reaction by adding water molecules to the opposite side. So for every oxygen atom that we need, we'll add a water molecule to the opposite side to give us that balance of oxygen. Since adding water molecules is going to add hydrogen to the equation, and put the hydrogen out of balance more than likely, we're going to add hydrogen ions next to balance out the hydrogen atoms that we just added through the water. And then finally, we are going to balance the charge in the half reaction. So we're going to evaluate what is the total charge on the reactant side, what is the total charge on the product side, and we're going to balance whatever that charge is using electrons. And the key trick there we always want to add the electrons to the more positive side of the reaction. It seems like a silly thing to say out loud because logically that makes complete sense, but it's worth saying because I can't tell you how many times I've gotten myself stuck. And the mistake being made was I was trying to add the electrons to the wrong side. Now, if we happen to be in base instead of acid, all that we need to do for each half reaction is just one more step. And that one more step is basically reversing the waters and the hydrogens. Switch their sides, turn the hydrogens into hydroxides since we're in base instead of acid. And then, like I said, once we've balanced each half reaction, we need to combine them together, but we need to combine them together in a way that there are no electrons left over. Because just like I said, kind of at the introduction here, oxidation and reduction are paired processes. They're independent yet dependent on each other. So there can't be any leftover electrons. So let's do some examples and some review just to kind of put ourselves into the proper frame here. So first, assigning oxidation numbers. Now, one thing one thing that we can notice, when we assign oxidation numbers, if we can recognize that we have an ionic compound like we do in the first two molecules, the first thing that we want to do is we want to split this molecule apart into the ions that make it up. So on the one side, I've got the chromate ion. Chromate ion is CrO4, -2, which means since this is a -2 charge, that must mean that the copper is a +2 charge. So if I'm assigning oxidation numbers, I've got a +2 on the copper. Now for the chromate ion, if you familiarize yourself with kind of the tips and tricks, you won't need to do this algebraic process every single time. You can just start kind of figuring it out in your head as you go. But at least for the beginning, we'll look. So we've got chromium and we've got 4 oxygens. And that has to equal a total charge of -2. Well, I know that oxygen is almost always -2. So if I put in a -2 for the oxygen, I could solve this out and I get chromium at +6 and oxygen at -2. How does that balance out? Well, copper 2 chromate has no charge overall. If I look at my oxidation states, it would appear, at least at first blush, that the sum of all those oxidation states would give us +6. But what I have to remember is that there are 4 of those oxygens. So the +8 from the 2 metals is balanced by the -8 from the 4 oxygens. So we are at a state of charge balance. We are adhering to that first guideline. So if you are stuck in trying to figure out what an oxidation state is supposed to be, turn it into an algebra problem. Take the molecule or the ion, break it into its pieces, elementally speaking, and set that equal to the charge. And if you do that, you should find that one or more of the elements inside of that compound follow very strict guidelines for charge, and we can use algebra to figure out the rest. For the second one, we've got magnesium oxide. Again, this is an ionic compound, so we're going to split it into its ions. We would have the magnesium ion, Mg +2, and the oxide ion, O -2. And since those are now just monatomic elements, their charge is their oxidation state. The magnesium would be a +2 state. The oxygen would be a -2 state. For hydrazine and 2H4, can't break it down like we did the previous two because it's not ionic. Since it's not ionic, we're going to have to go to the algebra for this. 2 nitrogens plus 4 hydrogens is going to equal a total charge of 0 because this is a neutral molecule. We don't have any specific guidelines on nitrogen, but we do on hydrogen. Nitrogen's a non-metal, so hydrogen's going to act metallic. So it's going to be +1. So 2 nitrogen is going to equal -4, which means nitrogen would be -2. So I've got a -2 from the nitrogen and a +1 from the hydrogen. All right, for the last one, we've got PCl3. Again, no ions here to speak of. So we're going to have to solve this algebraically. Now, here's a different kind of problem. In PCl3, I don't have any of the ions. I don't have any of the elements that have kind of fundamentally sound kinds of oxidation states. So what do I do? Well, what I do in that case is I defer to electronegativity. The element that is the most electronegative is going to take on its most familiar charge. So chlorine is more electronegative than phosphorus. Chlorine's natural oxidation state is -1. That's the state it would prefer the most. And since it's the most electronegative one there, that's the one it's going to carry. Which means that the phosphorus will end up being a +3 as a result. So when it comes to oxidation states, we just got to follow our guidelines. And that'll help us to figure out what exactly is going on inside of that molecule. So, kind of takeaways from this, if I'm looking at copper-2 chromate, seeing this chromium in a +6 state, that should kind of set off some alarms in terms of that's a pretty high oxidation state. I wonder how reactive the chromate is. And as we have seen in a number of circumstances in lab, chromates are pretty reactive to get that chromium down to a lower state. All right, any questions about oxidation numbers? All right, so let's take a look at this example problem here where we have to balance the reaction. Now, if we go through our process, the first thing that we should do is split it up into oxidation and reduction half reactions. Now, the only way to identify oxidation and reduction half reactions from the start would be to assign oxidation numbers. And if we did that, we would look at, okay, iodine's a +5, oxygen's a -2, -1 for the chlorine, 0 for the iodine, +5 for the chlorine, -2 for the oxygen. So it's pretty easy to see that the iodine went from +5 to 0. So that would be a reduction. And the chlorine went from -1 to +5. So there's our oxidation. So we could go about it that way. But like I said, we don't actually need to do this to figure out what's oxidized and reduced. So I'm going to leave it there, but we're going to prove it to ourselves otherwise. What we need to do is we need to break this up into a grouping, into pairs. So not that dissimilarly from how we identified acids and their conjugates in chapter 14, chapter 15. We're going to do kind of the same thing here. We're not really looking at conjugate acids and bases, but we're looking for atoms or molecules that are similar in their composition. And that's what's going to get paired up in these half reactions. So we can see that the iodate and the iodine are going to be one such pair. They both contain iodine in them. And the chlorine and the chlorate make up the other pair because, again, they both have chlorine in them as being in common. So 1/2 reaction is going to look like this. Iodate ion turning into iodine. Now, if we follow the process, we need to go through that series of steps, 4 of them in particular. First step, I need to balance everything that is not oxygen, that is not hydrogen. So in this case, that would be iodine. And I can see that my iodine is out of balance. I have 2 iodines here in the product, but only 1 here in the reactant. So I'm going to need a coefficient of 2 to balance out the iodates. Balance out the iodines. Second step, I need to balance oxygens. I do that using water. I have 6 oxygens on this side of the reaction. So that's going to take 6 waters to balance it out. Now I've got a balance of oxygens, but I don't have a balance of hydrogen anymore because I added 12 hydrogens where there were previously 0. So that's what I got to do on the other side. Twelve hydrogens become 12 hydrogen ions on this side now. So from an atomic standpoint, this equation, this half reaction, is now balanced. I've got 12 hydrogens on each side. I've got 2 iodines on each side. I've got 6 oxygens on each side. From an atomic standpoint, it's balanced. From a charge standpoint, it's not. And that's the difference between a redox reaction and a molecular equation. We've got to have that charge balance as well. Now, what do we do as far as that charge balance is concerned? Well, we need to evaluate. This side of the equation, 12 pluses and 2 minuses would be a total of 10 positive. This side of the equation, neutral, neutral, no charge. To balance the equation, I need to add to the more positive side the number of electrons that it would take to balance the 2 sides. So how many electrons does it take to turn a positive 10 into a 0? It'd be 10. So 10 electrons get added in. And this is how we can identify this particular reaction as a reduction reaction. We can identify it as a reduction reaction because this side of the equation, this half reaction, is using electrons. It is gaining electrons, and gain of electrons is reduction. Fundamental definition number 2. So I don't technically need the oxidation numbers to do that. It helps. It certainly helps because it tells us where the electrons are going specifically. But if I'm just trying to balance this out, I don't really need it. I'm actually okay without. Now let's look at the chloride reaction. In the chloride reaction, we've got chloride ion turning into chlorate. So starting from the top, I've got 1 chlorine on each side, so we're good there. I need to balance oxygens. 3 oxygens means 3 waters. The 3 waters gave us 6 hydrogens. So 6 hydrogen ions on this side. We now have atomic balance. We just need to settle charge balance. I've got a -1 on this side versus a +5 on this side. I need to add electrons to the more positive side. How many electrons does it take to turn 5 into -1? That'd be 6. So 6 electrons get added here. Now I have 2 balanced half reactions. I need to combine them together. But I can't just simply add them together yet, because I can see very plainly that this first process is going to require 10 electrons, but the second process is only going to give me 6. There's an imbalance there. So we can handle this a couple of ways. The easiest way is just to multiply each equation by the other number. Problem with that in this particular case is that you're going to end up with a reaction that is basically doubled everything. And you'll see it when you start to cancel stuff out. All the coefficients will end up being divisible by 2. What we're really looking for here is the lowest common multiple. Now, most of the time, we can find the lowest common multiple by multiplying the 2 numbers together. 10 times 6 would be 60. And so if I make the top reaction 60 electrons and the bottom 60 electrons, that would take care of the problem. Issue in this particular case is that there is a lower common multiple than 60, and that number is in fact 30. So what we need to do is we need to multiply these equations by a number to get the number of electrons to 30, which would mean 5 in the case of the bottom reaction, and 3 in the case of the top one. So when I do that, I will end up with 30 electrons plus 36 H plus and 6 iodates and 15 waters and 5 chlorides, turning into 3 iodines, 18 waters, 5 chlorates, and 30 hydrogen ions and 30 electrons. So that's the result when I combine everything together. Now, as I mentioned, as you can see, there is certainly some redundancy in this. The 30 electrons are common to both sides. We can cancel them out. The 36 hydrogens here are matched by 30 on the other side. So those 30 can go away. This would reduce to 6. And the waters on this side, we had 15 here, but 18 on the other side. So these 15 go away. These 18 reduce to 3. And so if I rewrite the reaction for acid, it would be 6 hydrogen ions, 6 iodate ions, and 5 chloride ions, turning into 3 iodine, 3 water, and 5 chlorate. So the end result here doesn't match nearly the mess that it took to get there. Because again, a lot of that stuff ends up canceling out on us. But what's important here is in the recognition of the process. And the process itself, yes, that problem took us a while to do. But as you become familiar with the process, you have to talk yourself through it a whole lot less. Now, what about the basic solution? Well, remember our guideline for base solution is basically we just take those hydrogens and those waters and we flip them around. So it's 3 water plus 6 iodate and 5 chlorides make 3 iodine, 6 hydroxide instead of hydrogen, and 5 chlorate. So that's the only difference. If you have to balance in base, you just got to do one extra step. You just got to flip the waters and the hydrogens around, turn the hydrogens into hydroxides. All right, let's take a look at one more example problem and then we'll take a break here. Write a balanced net ionic equation describing the oxidation of iron 2 by oxygen gas in an acidic solution. Now, this one's different just because we're being given less information. But there are some hints that we can kind of go off of that will help us along the way. We're talking about the oxidation of iron. Iron 2 plus. How many different kinds of iron ions do we know? What we really worked with thus far? We've worked with iron 2 and we've worked with iron 3. That's really it. We know that other oxidation states exist, but iron 2 and iron 3 are by far the most common. So when we're describing the oxidation of iron 2 plus, the most likely product is going to be iron 3 plus. And so if I need to balance this half reaction, Well, let's break it down. Iron atoms are already balanced. I have no oxygens to balance. I have no hydrogens to balance. The only thing left to balance is the charge. +2 on this side, +3 on the other. So I'm going to need 1 electron to balance the charge out. There's my half reaction. It's done. So like I said, they're not always complicated. Some of them are a good bit easier. Now, the other thing that we want to do, so obviously this is the oxidation half reaction. For the reduction half reaction, we're talking about oxygen, and the only hint that they give us is that water is a product. Well, let's take that and use it. In this one, there are no elements other than oxygen and hydrogen. So I don't need to worry about balancing anything else. I balance oxygens with water molecules. I've got 1 there, doesn't quite take care of it. What I really need here is 2. I need 2 water molecules to give me the oxygens that I need. Well, the next step would be to balance out the hydrogens with hydrogen ions. Since we're in acid, I have 4 hydrogens over here. I would need 4 hydrogen ions to take care of that. Total charge, no charge on the water side, +4 charge on the oxygen side. So I would need 4 electrons to balance that out. And yeah, that fits in with the narrative. The narrative is I've got a reduction taking place. Adding electrons to the reactants would be a reduction. So I've got my 2 balanced half reactions now. Before I combine them together, I got to take care of the mismatch of electrons being moved around. Oxygen can't get 4 electrons if the iron's only giving away 1. So lowest common multiple between 1 and 4 is 4. I need to multiply this top reaction by 4. And when I do, I'll get 4 iron 2 pluses plus 4 electrons, 4 hydrogen ions, and oxygen, turning into 4 iron 3 pluses, 4 electrons, and 2 waters. In this case, not nearly as much redundancy. The only thing that we have to pay attention to is that the 4 electrons cancel out. Everything else is the same. So the net reaction, 4 iron 2s, 4 hydrogen ions, and oxygen make 4 iron 3s and 2 waters. And that's it. That's all she wrote. That's the reaction in acid. Any questions about redox reactions, balancing oxidation numbers, that kind of thing? All right, let's go ahead and take a break then. And